Ever stop to think about what makes ChatGPT, Gemini, or, Claude so good at understanding and spitting back language?
Yeah, they're pretty incredible.
Well, get this.
Mhm.
Their abilities, it turns out, have a direct line back to a physics equation from 1982. Surprising, right?
It absolutely is. And that's exactly what we're diving into today. We're tracing this really fascinating journey of artificial intelligence, and believe it or not, it kind of kicks off with this single, seemingly unassuming equation.
Okay.
Our mission really is to unpack the foundational insight that let AI essentially remember things, and how that core concept is still driving the cutting-edge models we see today.
Seriously mind-blowing stuff. And the aha moment here is, well, it's huge.
Yeah.
This unexpected link between a physics idea, this drive to find the lowest energy state, and something like memory.
Exactly, a cognitive function.
Right. Okay, so where do we even begin to unpack this? How do we start?
Let's jump back to 1982, and let's talk about John Hopfield, a brilliant biophysicist.
Okay.
He came up with this equation E-A-T-E-S-C-A, we a essay, which, at first glance, it looks like something straight out of condensed matter physics.
Yeah, it does look pretty physicsy, but you mentioned it's like a Rosetta Stone for associative memory. What's the key there?
Okay, so think about it like this. Each psi and swi, those are like basic units. Maybe think of them as neurons, either active or inactive, like a switch. +1 or -1.
On or off?
Simple. Simple. And the we part, that represents the connection strength between these units, like how strongly two neurons influence each other.
Okay, the synaptic weights.
Exactly. Now, the clever part of the equation is it calculates the overall energy of the whole network.
Hmm.
And the network then naturally tries to find a state where this energy is as low as possible.
Okay, so it's like a system trying to relax,
Mm-hmm.
to find its most stable configuration. Like if you drop a marble into a bowl, it just rolls to the bottom. Is that the kind of idea?
That's a perfect intuition. Exactly that. Imagine feeding a fuzzy image or maybe a jumbled sentence into this network. The system then starts adjusting itself internally, flipping those states.
Right.
And because of how those connections, the Ouija's, are set up by the equation, it eventually settles. It finds a stable, low energy state. And that stable state, that's the clear recalled memory, like the marble finding the bottom.
That's incredible. So a physicist basically figured out that thinking, or at least remembering, could be understood using principles from thermodynamics, like the collective behavior of lots of tiny interactions.
Pretty much, yeah. It was a revolutionary worldview at the time. Cognition as thermodynamics.
Where did he get the inspiration for this? It seems like such a leap.
What's really insightful is that Hopfield drew inspiration from spin glass theory. It's a concept in physics.
In glass, okay.
Yeah, in spin glasses, individual atoms act like tiny magnets. They can point up or down, spin up, spin down. He saw this analogy with neurons being either on or off, +1 or -1.
Okay. The binary states.
Exactly. And the core operation in his network was surprisingly simple. You basically flip the state of one neuron from on to off, or off to on, and you check. Did the system's total energy go down?
Right.
If it did, great. The network tends to keep that change. If not, maybe flip it back. And you just repeat this process, neuron by neuron, until the whole network finds a stable point, a minimum energy setup.
Wow. So this really basic process, just flipping and checking, that could lead to something as complex as recalling a memory. That's the whole emergent behavior thing we hear about, isn't it?
Precisely. Hopfield showed that complex behavior memory, in this case, could emerge from these very simple local rules and interactions, no central controller needed. And, if you look at the big picture, it's pretty striking. Modern AI, even the really powerful transformer models, they're still doing something fundamentally similar.
Still seeking low energy.
Yeah, they're constantly searching for low energy states, though we usually call it minimizing loss nowadays. The terminology's evolved, sure. We talk about things like layer norm now, which helps stabilize the energy levels, you could say, across the network.
Okay.
Or positional embeddings, which help the network understand the sort of energy related to word order, but the underlying principle, a system seeking stability. That remains remarkably consistent.
So before Hopfield, early AI models, they struggled with memory. What were the limitations?
They did, yeah. Robust associative memory was a real challenge. Hopfield's big contribution was proving that memory could be directly encoded right into the network's connection strengths, those we values in the weight matrix.
Okay. Not just computed, but sort of baked in.
Exactly, baked in. It meant retrieving a memory or completing a pattern if you only had part of it. It wasn't just some abstract computation, it became a physical process. The network literally settling into a predefined energy minimum, a groove it had learned.
That really makes that phrase, neurons that fire together, wire together, feel much more concrete. Like those connections physically create the memory landscape.
You've got it. It provides a physical basis for Hebbian learning, essentially. And his networks, they weren't just theoretical toys. They could actually store multiple patterns.
Right.
And you could test them, give them a fragment, a piece of an old pattern, and see if they could recall the whole thing. Recovering from partial information, that was a big deal.
You mentioned earlier the equation feels physical. Can you expand on that intuition a bit?
Sure. Think of those neurons, those Cs, as tiny magnets again. And their interactions, the weege, think of them like tiny springs connecting the magnets.
Okay, springs.
If the springs are stretched or compressed too much, maybe because connected magnets are pointing in opposite directions when they should be aligned, the whole system feels, stressed. It's in a high energy state.
Right, it wants to relax.
Exactly. Minimizing the energy according to the equation is like letting those springs find their natural, unstressed length, where everything clicks into place, finds equilibrium. That's the low energy state.
Okay, yeah, the marbles in the cereal bowl analogy comes back. Shake it up, high energy, lots of bouncing, then they settle in the bottom. Low energy, stable.
Perfect analogy. And it's really the same core intuition that powers gradient descent. That's the main optimization algorithm we use to train basically all modern deep learning models. We're always trying to find those low stress states, those valleys, in this huge high dimensional space of possible parameter settings for the model. It's like the AI is constantly feeling its way downhill.
You've got some great analogies. Can you give us another one just to really visualize this AI memory idea in action?
Okay, how about this? Imagine your fridge is covered in those magnetic letters spelling out words. Now, if you bump the fridge hard, the letters might get all jumbled up, right? High energy state. But when things settle down, because certain letters have a stronger magnetic attraction to their old neighbors, maybe familiar words start to snap back into place on their own.
Ah, I see. The jumbling is like noisy input.
Right. And the words reforming, that's like the network settling back into a known memory state, a low energy configuration. It's a very simplified picture, but it captures the essence of how these associative memory networks work.
I like that. The magnets finding their friends again.
Or here's another one. Think of a jigsaw puzzle, but imagine it's in a magic box. You toss in all the scrambled pieces, give the box a good shake.
Okay.
And then you start hearing these little clicks as the pieces somehow slide around and find their correct neighbors, eventually forming the complete picture. Hopfield basically showed us the physics of how such a self-assembly process could happen. It's the system minimizing as energy, or in today's AI language, its loss, finding the state where the pieces fit best.
It's almost hard to believe this foundational work happened way back in '82. Yeah. And speaking of recognition, didn't John Hopfield just recently get a major award for this?
He did, yes.
Yep.
In October 2024, he was awarded what many people are calling the AI Nobel Prize, along with Geoffrey Hinton. Hopfield's part was specifically for this fundamental work connecting those atomic spin models from physics to how memory retrieval works in neural networks.
Well,
the award citation literally highlighted how his equation links atomic spin models to memory retrieval. So it's not hyperbole. It underscores just how significant his early discoveries were. Without Hopfield's work, Hinton's subsequent big step, the Boltzmann machine, might not have happened when it did or how it did.
I think I saw the citation was even titled something like How One Equation Changed AI. That really does hammer home the impact.
Exactly.
It sounds like a real chain reaction. Each generation of AI research building directly on the shoulders of the previous one, all stemming back to Hopfield's insight.
Absolutely. It really is like a relay race of innovation. And we can actually sketch out a sort of simplified family tree, if that helps.
Yeah, let's do that.
Okay, so it starts with the Hopfield network, 1982, deterministic energy minimization. Then, pretty quickly, you get the Boltzmann machine around 1985, Hinton and Sejowski. That added temperature, stochasticity, hidden units, made it more powerful but harder to train.
Right. Temperature lets it jump out of bad local minima.
Exactly. Then things simmered for a bit, but in the mid-2000s, we got the restricted Boltzmann machine, or RBM, simpler structure, easier to train.
And those could be stacked, right? Leading to
deep belief nets. Around 2006, that was Hinton again, Bingio, LeCun, using RBMs for unsupervised pre-training. That was a huge breakthrough for deep learning.
I remember that era. That really kicked things off again.
It did. Then, from around 2012 to 2016, we saw this big wave of convolutional nets, CNNs for images, and recurrent nets, RNNs, LSTMs for sequences. Huge progress there.
Yeah, ImageNet speech recognition.
Right. And then the next massive step, 2017, the transformer architecture. Attention is all you need.
Yes. The attention mechanism.
Which directly paved the way for the large language models, the LLMs like GPT, BERT, and all the ones we know today, starting roughly around 2018 and continuing strong.
Looking at that timeline, you really see the lineage, and you're saying all the way through, even up to today's LLMs, that core principle, finding stable states, those low-energy basins, that still applies. It all traces back to Hopfield.
Fundamentally, yes. Even with these incredibly complex LLMs, a pre-training process, it's basically the model navigating this unbelievably vast and intricate loss landscape.
Loss landscape, right.
And gradient descent, the training algorithm, it's acting as the guide, gently nudging the model's parameters, billions of them, to find the valleys in that landscape where its predictions match the training data best.
So we swapped energy for loss, or technically negative log likelihood.
Exactly. Different name, slightly different mathematical formulation, but the core concept. Seeking stable, low-value configurations. It's the same intuition.
So when ChatGPT auto-completes my sentence, it's like it's rolling downhill in this enormous landscape to find a phrase that sits in a comfy, low-energy valley of probable language.
That's a fantastic way to think about it. Imagine GPT-4's parameter space, all its possible settings, as being like the Grand Canyon. Just unimaginably vast and complex.
Okay.
Training it is like trying to hike down to the riverbed, maybe blindfolded, but you can always feel which way is down. That feeling of down is the gradient. Those paths lead to the valleys, the attractor basins, where the model's understanding and generation of language gets really good. Hopfield's idea of attractors just scales up massively.
That gives such a different perspective. Can we bring it back down to earth? More everyday examples of this principle.
Sure, think about your phone's autocomplete. You start typing peanut butter
And it suggests jelly. Or maybe banana.
Right. That suggestion is like the system quickly falling into a nearby, very common low-energy valley of word association based on vast amounts of text data it's seen.
Okay, that makes sense. What about something like Netflix recommendations?
Similar idea. Services like Netflix use complex models, but they effectively build Hopfield-like memories of your viewing history, what you watched, liked, skipped, time of day.
Mm-hmm.
The lowest energy valley for your recommendation tonight might be, say, a sci-fi movie, because that aligns with strong patterns in your past behavior. It's completing the pattern of what you might like.
And voice assistants, like asking Alexa or Siri.
When you say, hey Siri, play Bohemian Rhapsody, the system is essentially taking that partial pattern, your voice command, and completing it by finding the best match, the lowest energy state within its massive knowledge base of songs, artists, and common commands. It settles on the Bohemian Rhapsody memory.
So even though the tech seems light years away from 1982, and the math is way more complex now, that basic principle of settling into a stable memory state is still hiding under the hood. Why is Hopfield's original work still seen as so foundational?
Well, for several key reasons, I think. First, it just gave us this clear, conceptually powerful way to think about memory. Not just static storage like a file on a disk, but as a dynamic process of settling.
Right, the process.
Second, the architectural ideas, networks of interacting units, energy functions, they've had echoes in so many later developments. Denoising autoencoders, Boltzmann machines, obviously, diffusion models for image generation have connections. Even parts of the transformer architecture arguably relate back.
Interesting.
And third, it really built this vital bridge between physics and AI. Physics offered these powerful conceptual tools and mathematical frameworks, and in turn, AI started posing new questions for physics about complex systems. That cross-pollination is kind of super important.
It sounds like this interplay, physics meets AI, especially for things like language, that's not over yet.
Oh, absolutely not. We're seeing really exciting potential now in areas like quantum annealing or quantum-inspired algorithms. They might offer entirely new ways to search those energy landscapes and find even better solutions.
Quantum AI?
Potentially, or at least quantum-inspired classical algorithms. Plus, there's tons of research into neuromorphic chips, hardware specifically designed to mimic neurons and synapses, often implementing Hopfield-like attractor dynamics directly in silicon. Very energy efficient.
Right.
And even things like analog photonic networks using light to do computations could offer super fast ways to solve these kinds of optimization problems. Imagine tiny, ultra-low powered devices that have a kind of continuous, always-on Hopfield memory, maybe working alongside a small, efficient transformer for specific tasks.
The future sounds like Integrated physics and AI.
Yeah, it feels like AI development has this fractal pattern. We keep zooming in and finding variations of the same core principles, like energy minimization, reappearing at different scales and in different forms. It constantly loops back.
Okay, I have to admit, even after all this, that original equation, E12 yay, way, cis J, it still looks a bit intimidating if you're not a physicist. Is the math really that approachable?
Well, the formal notation can look dense, sure. But the underlying idea, the principle of minimizing energy, that's something you do intuitively all the time.
Like how?
Okay, imagine you walk into a noisy, crowded cafe and you want to find a table to have a quiet chat. You scan the room, right? You instinctively look for a corner away from the speakers, away from the big loud group. You're naturally seeking the spot with the lowest noise energy.
Okay, I do that.
See? You're intuitively solving an optimization problem. Hopfield's equation just gives us a precise mathematical way to describe that kind of drive towards stability, towards the quietest table in the system's state space. You already get the core concept, even if the symbols look weird.
Okay, framing it like that helps.
Mm-hmm.
So let's try to really nail the connection. Can we simplify how the building blocks of today's LLMs, like GPT, connect back to Hopfield's core ideas, without getting lost in the weeds?
Let's try. So transformers, at their core, do a few key things repeatedly. First, they take words and turn them into lists of numbers, vectors, embeddings.
Right, embedding words.
Then comes the crucial part, attention. Each word's vector effectively looks at all the other word vectors in the sentence, or at least the recent context. It calculates how relevant each other word is to it.
Okay, figuring out relationships.
Exactly. Based on that relevance, it creates a new, updated vector for itself, blending information from the important neighbors. Then it does some further processing, and this whole sequence repeats layer after layer.
So where's the Hopfield connection in that?
That attention step, where each word is interacting with others based on relevance, that's like the modern, super sophisticated version of those pairwise Weege interactions in Hopfield's network. The springs connecting the magnets.
So instead of fixed springs, the connection strength, the attention, is dynamic. It changes depending on the specific words.
Precisely. It's much more flexible. And you could even think of the individual neurons or magnets in Hopfield's model as being analogous, in a very loose sense, to the attention heads within a transformer. Each may be looking for different kinds of relationships or patterns in the input.
Okay, that clicks. The basic idea of interacting parts settling towards a meaningful state persists, but the mechanism got way more powerful.
You got it. The fundamental intuition carries through.
You mentioned a really simple non-computer demo for this, the paperclip thing. Tell us about that.
Oh yeah, it's a neat little illustration. You take, say, 20 paper clips, label half A and half B with a marker.
Okay.
Then just randomly tie them together with short bits of string, make a tangled mess.
Got it. Tangled paper clips.
Now, here's the trick.
Oh.
Whenever you find an A tied directly to another A, pinch the knot between them, tighten it a little, do the same for any B tied to another B. Don't tighten the knots between an A and a B.
Okay, reinforcing like-likes.
Exactly. Now, if you carefully pick up this whole jumble and give it a gentle shake, let it settle, you'll usually see the A clips start to clump together and the B clips clump together. They physically separate.
Whoa, really?
Yeah, it's a physical manifestation of the system finding its lowest energy state. The tightened knots pull the similar clips closer. It's like a physical Hopfield network finding two attractors, the A memory and the B memory. No computers needed.
That's brilliant.
Yeah.
Such a tangible way to see the principle.
Yeah.
So, thinking about this from the inside, what does memory feel like to a machine running on these principles? Can we even guess?
That's a deep question, but maybe we can use analogies. Think about how a certain smell, like sunscreen, can instantly trigger a whole cascade of summer memories, right? A tiny cue unlocks a big pattern.
Yeah, definitely.
A well-trained Hopfield network works similarly. You only need to give it a small fragment, a few neurons from a stored pattern, and the network dynamics will often complete the rest, falling into the full memory state. And you know that tip of the tongue feeling? When you know something, but just can't quite retrieve it.
Yes, all the time.
That could be analogous to the network state being temporarily stuck on a ridge in the energy landscape, balanced between two or more memory valleys, unsure which way to fall.
Wow.
And maybe that gives us a tiny intuition for why LLMs can sometimes be so sensitive to prompting. The prompt nudges the system into a particular region of its vast state space, influencing which memory valleys are easiest to fall into next.
It really does all seem connected in this weird, fascinating loop. And it highlights how AI progress isn't just these sudden eureka moments, but this continuous layering, building on past foundations.
Exactly right. It's often described as disciplined tinkering. Hopfield adds the physics foundation. Hinton and others figure out how to add depth and probabilistic reasoning. Vaswani and team introduce attention. The next layer might involve something totally new, maybe ideas from quantum physics, maybe something else entirely.
But the older layers still resonate.
They do. Those core principles, like Hopfield's energy minimization, they ripple through. They influence how we design the next generation of architectures. Today's transformer design quirks might become the foundational assumptions for whatever comes next. And sometimes revisiting those old ideas, the unanswered questions from decades ago, can spark entirely new research directions.
So bringing this amazing deep dive full circle, tracing this line from today's most advanced AI all the way back to that single physics equation from 1982. What's the big takeaway, the main thing you want listeners to remember?
I think the central point is that John Hopfield's work, using concepts from physics, gave us a truly fundamental and remarkably durable way to understand how systems, artificial ones included, could learn and recall information associatively, how they could remember. It really laid a crucial piece of the groundwork for the sophisticated AI that's becoming so embedded in our lives now.
Yeah.
Everything from, the simple autocomplete on your phone to the really complex language understanding in chatbots like Gemini or Claude owes a conceptual debt to that 1982 insight.
It's just an incredible journey to think about. That leap from abstract physics to everyday AI tools.
It really is. And maybe it's a good reminder, that sometimes the most profound real-world impacts come from these seemingly abstract mathematical or scientific ideas. Who knows what other simple-looking formulas are hiding in plain sight right now, just waiting to unlock the next AI revolution.
Something to think about.
Definitely. So keep an eye on those metaphorical marbles rolling downhill, both the ones in physics labs and the ones inside the algorithms. You never know what insights are waiting in those low-energy valleys.